Hey, welcome to my video. My name is Patrick. I'm a data scientist in Toronto, Canada. Welcome to the first episode in my Code Along video series where I walk through different data science, machine learning, and AI projects. I want to use this series to explore different machine learning ideas I've accumulated, partly for myself, but to also maybe help give people an idea of what data science is like from the data processing, machine learning, and modeling side of things. The ultimate goal for today's episode is to develop an agent that plays Connect 4 and does better than a random bot. So the bar is pretty low here, but in the next video, we'll get into refining and tuning the neural network to improve performance toward maybe optimal play. So for our Connect 4 reinforcement learning agent, we first give a background on what Connect 4 is. Connect 4 is a board game played between two players where each player takes turns placing checkers into a grid of 6 rows and 7 columns. The player who places their pieces first to connect 4 in a row, either horizontally, vertically, or diagonally, wins the game. And this grid can be expanded with a larger board and different connect end requirements, but we stick to the traditional 6x7 Connect 4 format that you'll find in normal board games. I'm going to build the game with Pygame. We'll go over some of the Pygame basics and the game mechanics that we have to implement for Connect 4. We'll also go over reinforcement learning, some of the basic components, deep Q learning, and our training implementation. We'll go over some of the simulation results as well in terms of the RL bot against a random bot, against itself, and using self-play, as well as discuss maybe a few future improvements for a future video. So building the game, a lot of what you'll see on screen now is me coding up, developing the game. The game is implemented from scratch using the Pygame library in Python. Pygame, in a nutshell, initiates a game window to render objects and images of the game. Essentially, games are just collections of individual frames, and in each of those frames we look for certain events to happen, like keyboard presses or mouse button presses, and we do certain things based on what keys were pressed or where a mouse was clicked. For example, an event can be when the mouse is moved across the game window, or when it's pressed, the mouse's coordinate position on the screen that we define is recorded. And in the case of Connect 4, we can compare that against the columns of the game board in order to determine which column we should place a new piece in. Here's the pseudocode for the main Pygame loop. We start a while loop, and this is essentially for each game. For every, let's say, frame or iteration of this while loop, we will render any pieces on the board, render the board itself, and then render the scores. And then we'll take the clock forward 60 frames. And here we check if the game is done, and then we do a whole bunch of other stuff. But while we're running this loop, we're checking any event that occurs that Pygame is able to record. We check, if there's a quit, then obviously just quit the game. But if there's something like a mouse button down for human players, then we have to calculate the column on the board based on the mouse press coordinates, and then we place the piece and check the Connect 4 win condition, and then go about all these rendering items. So it's pretty basic. Here we'll also bake in the random bot or the reinforcement learning bot to make the move if it's not a human player's move, for example, or if it's just bots going against each other, then they'll kind of take turns going back and forth. So pieces are stored as class objects, and the piece images themselves were made in Canva, and I transferred those over to GIMP once they were prepared, and then just converted them to transparent images using the convert to alpha functionality. These pieces are stored in the program as follows. So they're just prepared as simple data classes. They only have 2 attributes, turn and coordinates. I'm denoting turn as an integer, either -1 or 1 for the red or yellow pieces. And here we store a list of the placed pieces. Anytime we place a piece, we will append to this list the actual placed piece. Based on this dictionary that we define, we can load the images of the red piece and the yellow piece that we created in Canva and GIMP. And we just load it in once and store it in a dictionary. And then anytime we need to call them, we basically can use this display.blit function, call the dictionary of images, and basically take whoever's turn it is, grab their image, and then load it up with Blitz using the piece coordinates, and this is done for every piece in the placed pieces list. In terms of the board representation, this is a 2D NumPy array, and we store it in board array. It first contains zeros, but then whenever a piece is placed, the array is filled in with 1 at the corresponding coordinate. And in addition to this, 2 separate arrays are maintained, which represent only the pieces for the red and the yellow players. So these arrays then are summed up to equal the board array, and these are specifically used for state matrices, which we'll get into the RL network, since a reinforcement learning bot would need to know which pieces are friendly versus enemy pieces, for example. And then for piece arrays for the red and yellow pieces, we do a zeros like, so this is just making an identical array just like board array with the same dimensions, but filling it with zeros as well. We load the board image that we made in Canva and GIMP using pygame.image.load, and we store it in board image. And then we render the board at every tick of the clock using the same display.blit that we used for the pieces. And this is going to be at coordinates 0, 0, which is the top left of the screen or the game window. The logic then to place the pieces and update the board and the piece arrays is as follows. So anytime a human player or a bot makes a move and decides on which column to place a new piece, we first check if the move is legal. For example, that the selected column is not already full. For the RL bot, we determine that any illegal moves result in just a loss or a win for the other side. This was the easiest solution to kind of circumvent this and have our bot learn not to make illegal moves. If there are no pieces in the selected column, then we place the piece at the maximum index, which is at the very bottom of the 2D array. And if there are already pieces in the column, then we place a piece using the np.argmax -1 of the column. And np.argmax basically gets the index number of the largest value in the column, and it grabs the first value that occurs. So that would grab the top of the column in the board. Next, we update the piece arrays for the current player and the board array with 1 at the coordinate so that we're always keeping track of the new pieces that are placed. And then we also check if there's a connect 4 win condition or if the board is full of pieces. If there's a connect 4, then obviously we return a win for the current side who just placed the piece. But if there's no connect 4 and the board is full, then we return a draw because there's no other slots to place pieces in. Otherwise, we return none, which signifies that the game is still ongoing. Now, in order to check for the connect 4 win condition, the function check connect 4 piece crawls in all directions of a newly placed piece to check if any of the neighboring pieces linked up to 4 or more. There are 4 directions to check in total, which correspond to one-dimensional, let's say, direction vectors. The 4 directions are basically horizontal, vertical, and I'm calling them diagonal 1 and diagonal 2. So when we place a new piece, whether it be a human or a bot, at that coordinate of the newly placed piece, we can just add and subtract these vectors for each direction to get the coordinate of the slots to check next. So for example, if we place a piece at 3, 3, for example, position on the board, then in order to check for connect 4, we'll do the following. So first we can check the horizontal direction. So this is the 0, 1 vector. And then we add this vector to our current coordinates, which is 3, 3, to get the slot on the right-hand side. And then we also subtract the vector from 3, 3 to get the left-hand side slot. Therefore, we check 3, 4 and 3, 2. If the left slot, so coordinate 3, 2, doesn't contain a friendly piece to continue the chain of pieces, then we can stop searching the left side entirely for this direction, which is horizontal, and we do the same thing for the right side search. But if the left slot or the right slot does contain a friendly piece, then we can continue the search just by subtracting the vector once more. Therefore, we now check 3, 1 instead of 3, 2. And similarly, we do the same thing for the right-hand side. We continue this search until both the left and right hand sides have become exhausted, or they come across dead ends like enemy pieces or empty slots. And once both sides, left and right, have come across these dead ends, then we stop the search in the horizontal direction and we sum up the number of friendly pieces that we found so far in this search. We repeat this search for the 3 other directions, vertical, diagonal, and diagonal 2. And after all the searches are done, we just check if any of the sums for each of these 4 searches that we did are greater than or equal to 4. So this is a pretty basic search algorithm to check if connect 4 is on the board, and this is the implementation. For initial testing purposes, we instantiate a bot class that selects a random column to place a piece from the available columns on the board. So the implementation here is pretty simple. We initiate a player class, and then from the bot class, which inherits from player, we have a move method which checks for the available columns, and then we just take a random choice of those available columns. In the main Pygame loop, if the current player is a bot, then we just grab the column that the bot wants to move to based on this method, and then we simply place the piece in that column. So reinforcement learning, there are three primary classes of machine learning, which include the following. Supervised learning, this is learning from a dataset that is labeled with a target, and the goal in training is to predict that label or target. A label is supplied for each data instance to serve as the ground truth, and models aim to minimize the error of their predictions against this ground truth so that they can learn and hopefully generalize to new samples. For example, input data might be information on houses like the neighborhood, category maybe, square footage number, the number of bedrooms or bathrooms, and the label to predict might be the house price. And you can imagine how these variables might affect and enable prediction for such a label. But this is an example of having an actual label to inform our learning. Unsupervised learning, on the other hand, learns from unlabeled data to find meaningful structure. So input data might be retail store sales data, where every sample is a customer's basket of purchased items. A model can be developed to learn from this data and maybe group customers into some number of categories based on the types and frequencies of items they purchase. Such a model might organically cluster customers into groups like high income or low income, or if they're a parent or a non-parent, without the need for the data scientist or ML developer to create or search for these clusters. Unsupervised learning is helpful for exploratory research and exploratory analysis, but it's different from the predictive goal of supervised learning. Now, reinforcement learning, on the other hand, is the goal of learning the optimal actions to take in an environment where the states and rewards for each action are observed by some model or an agent. An agent interacts with an environment and then takes some action, which then gets it rewards, and the agent learns based on past experience to make better decisions over time. And the clear example for us is playing board games like Connect 4 or chess. So in the components of reinforcement learning, it involves several components that are defined uniquely for each RL problem. In simple terms, a problem can be defined as an RL problem if there is some notion of state in the environment that can be passed to an agent, and the agent then must take an action by following some kind of policy. And we'll get into the definition of all these guys in a bit, but this produces some kind of reward and consequently a new state as a result of that action. The learning that occurs is when an agent updates its estimation of how valuable each move is in each possible state based on the rewards that it receives taking those actions. If we're in some kind of state, we just want to know what kind of action to take so that we can maximize rewards that we can receive in the future. To get into the definition of some of these guys, state is some representation of the environment for which the agent lives in and must make decisions in. So in our case, the state is represented by the board array and the piece arrays. This is just 2D arrays denoting where certain pieces are on the Connect 4 board. So here is the board array 6x7, and we have a few pieces placed here denoted by 1s. The piece arrays are split into two separate arrays here, and for the purposes of simplification and computation in the neural network, we reshape this into a one-dimensional tensor or vector of 6x7x2 elements. So basically we take the rows of all of these arrays, file them up all in a line, and we do the same for the yellow pieces, and then we just append those to each other. And this gives us a representation of the current state for the RL agent. This is a view into the RL bot implementation. Here we get the state arrays and we process the states. When we make a move, we receive the piece arrays, which are these two arrays for the red and yellow pieces, and then we process them into a single 1D vector. We grab what are called the Q values, or the estimates of how valuable each action is, by passing the state through to the model and generating predictions on those states, and we'll kind of get into what that looks like in a bit. And then we grab the action, which is the action with the maximum value, and we just return that action to make a move on the board. So the agent is simply some mechanism that interacts with the environment to receive the states, rewards, and the next states for the purpose of learning. In our implementation, our RLBot class effectively acts as this agent because it encapsulates our neural network model, our move generation logic, and the training loop. This class is also the object to be called by the game environment whenever it's the RLBot's turn to make a move on the board. The available actions we can take in Connect 4 are simple, since the agent only has 7 columns available to decide where to place a new piece when it's the agent's turn. In our implementation, our agent basically selects a column between 0 and 6 to denote the index of the column to place a new piece. A policy defines the agent's behavior at a given time or state. This essentially represents a mapping of states to the actions that an agent should take. For example, for a self-driving car, a very simplistic policy might be to take the action accelerate if the state or the road condition is clear of obstacles. Though obviously this is not a very good or safe static policy to set in a self-driving car. The policy we select for our agent is to generate the estimated values of taking each action. Just take the action with the highest estimated value, but with one caveat. We set some epsilon value, so this is some kind of float number between 0 and 1, and we take a random action instead of the highest estimated value some epsilon % of the time. The reason we do this is to invoke what we call exploration in the RL agent. This is because we need to incentivize the agent to explore novel and different moves in different situations in order to ensure that there's a comprehensive learning of the game. We essentially want it to make different types of mistakes and make novel moves that might very well end in disaster or might actually turn out to be very fruitful. This is because for the network to estimate values, we have to randomly initialize parameter weights in the neural network. This can cause learning algorithms to get stuck in local minima, so it never really gets out of its own hump, or it's kind of just confirming itself and its own initialized values, when really we want it to gain an overall picture of the game and to really find the global minimum as it pertains to maximizing the rewards of the game. Another snippet into our RLBot class, we set an epsilon value of 0.2, so 20% of the time we'll take a random move, but 80% of the time, which is 1 minus 0.2, we'll select the move that we estimate as the highest value for the action to take. So in the move function, we have the Q values, which are basically the predictions from our model. And then if some random integer is less than epsilon, then we select a random integer from 0 to 7. These are the columns of the board. Otherwise, then we select the argmax of the Q values that we estimated up here. So this is called exploitation. In order to estimate the values of each action in each state, a value function must be used. And we've been talking about, okay, the model predicts the values for each action and gets the highest value action. Well, how do we do that exactly? In this project, we use deep reinforcement learning by incorporating a neural network as the value function estimator. And really, the value function estimator can be a lot of different things. It's quite flexible in terms of how you incorporate this kind of function. It's essentially a function that takes a state and maybe takes an action and gives you some kind of value for it and says, okay, this is worth this much. And in our current method, we use a neural network, which is a fairly basic one as well. We feed the neural network with the state representation vector, which is this 1D vector, and we receive some kind of output with 7 elements, and these correspond to the columns on the Connect 4 board. So we output a vector of size 7, which denote to us how valuable the model thinks each column is. And in this case, these are just random numbers, but maybe the last column here with 0.7 is the most valuable, so we should take that. So this is the neural network implementation in the RL bot class. We have a whole bunch of parameters here. So we define activation functions, we initialize the model itself. So here we're basically just using a very simple layout, 84 nodes or 84 items. We have a hidden layer of 150 nodes, another hidden layer of 100 nodes, and an output layer of 7 nodes. And the model itself, we use Torch sequential model. And we have the first linear layer. We have an activation between each of the layers, and the final layer outputs the vector of size 7. So in terms of rewards, these are essentially numerical signals that teach an agent which actions are favorable and which are not. These can be defined in a number of ways and can also be treated as a hyperparameter for tuning. For example, if we want an agent to perceive certain losses or situations very negatively, then we may opt to give a very large negative reward as a sort of bigger slap on the wrist. For a board game that reaches episodic conclusions, i.e. the game ends with a winner or a draw, we can define the rewards based on whether the agent made actions that resulted in a win, a loss, or a draw. So during the game, if the game result has not yet been decided, then rewards might be defined as 0 for every move, but some games we can maybe set up to give negative rewards to agents for every move that they make, and doing something like this might motivate agents to learn quicker methods of reaching the end of an episode. So our reward system is pretty basic. We have a draw condition which rewards 5 points. If the agent wins, then it gets 10 points, and if it loses, then it gets minus 10. And for every move that doesn't result in any of these, then it just gets 0. So I think the burning question is, how exactly do RL models learn? Where does the learning happen? And deep reinforcement learning requires us to update the parameters of our value function, so the neural network we showed earlier, in order to learn better estimations of the values of the actions. So in order to do this, we use deep Q-learning. Q-learning holds that the value of taking some action A in a given state S should be equal to the reward R received by taking that action, plus the value of the next action in the next state. This is because when we take action A, this will lead to the inevitable new state S prime, where we will make another action, A prime, that should represent the best action at that state. The formula for Q-learning is shown below here. We have a Q value of the current state and the action that we just took. This is equal to the reward we received in this state, taking this action, plus the maximum Q value of some future action that we'll take in the next state. This gamma value represents a discount factor that discounts the importance of these future rewards, so this new state and new action. And conceptually, a gamma value of 0 would cause the right side of this equation to equal 0, because this would be 0, meaning that the agent would only value the current action it's taken by the immediate rewards that it receives. This causes it to be very short-sighted, and you can imagine in a game like chess where, let's say there's checkmate in 2 moves. If the bot only sees 1 move ahead and only wants to take very short-sighted moves, then it might miss the planning opportunity to prevent checkmate in 2. Ideally, we'd like RL agents to take actions that lead to higher values on the bigger scale or in the long term, as opposed to just the current move, because that's effectively how you win these games like Connect 4 or chess. It's also how you drive a car. It's also how you make better decisions in a lot of RL problems, is not in the short term, but in the long-term planning process. And this is what we want our bot to learn. So our implementation of Q-learning in our training loop is as follows. We have the class here with all the lovely parameters. We have a training loop function every time we place a new piece and then get a new state of the board. So every time we move, basically. We process the state into the one-dimensional vector we've been discussing. We get a reward first, so this is based on the mapping we defined, and then we get the estimated Q values of the new state. So we're basically using this function here to generate the new values. So for the new state, we feed this into our new model, and then we get the highest value based on those predictions. And here we use the Q-learning function. So y, which is going to be the target value, is going to equal reward if the result is not none. So if the game is over, then there is no new state here to add. So it's basically just going to be this side of the equation. So if the result or the game is over, then y is equal to reward. Otherwise, y would be equal to the reward plus self.gamma times the maximum q value that we defined up here. Based on the action that we just took and the reward we received for it, plus the future value that we should expect to receive, this should be what our value estimate is for the current action. However, what does our current model say? What is our current model tuned to predict? And how far off is that from this new estimate that we're making? So that's why we're comparing y and x. So we already have some kind of estimate of the value of the action we're taking. This is because we made a move based on the highest Q value that we estimated at the time. So here's a nice little description of the training loop. We gather the estimated future Q value, which is denoted as y, and we compare it against our original estimate of this Q value denoted by x, and we use the loss function here. The loss function is basically a fancy function that compares two values and outputs how far off they are from each other. So it typically outputs larger values if our estimate of Q was like way off from what Y should have been. Let's say our loss function outputs a very large value, which means that our network was very wrong in estimating the value of action it just took in the current state. That means that theoretically we have a lot of learning to do, right? There's a big adjustment that we have to make in the network parameters. And therefore, after calculating this loss, we perform backward propagation, which is essentially just a way to take this loss value, so the amount of error we made, and we attribute it to the different nodes in our neural network. So we basically say, okay, which parts of this network were most to blame for this error? Then we can start updating the parameters of our network so that for future instances, our model will just be slightly better. It'll start to make slightly smaller errors or loss values for the future prediction. And this is effectively what learning is in neural networks. So let's take a look into some of the results of the simulations to see how well our bots are performing. These are the aggregate results for our simulation runs. The first 4 rows are the training simulations, and the last 3 are the testing simulations. These ones we don't run the training loops, so we don't update any parameters, and we're essentially just seeing how well the bots perform against a random bot as just the proxy comparison. In this first sim, we're using random bots to play against each other. Obviously, this is as you'd expect across 1,000 epochs or games. We are seeing a 50% win rate, so that's just as expected. When we have our RL bot play against a random bot, we see a 73% win rate. When we play 2 RL bots against each other, 2 separate RL bots, by the way, where their parameters are initialized separately and they learn kind of on their own by playing against each other, we see a 50% win rate. Effectively, it is kind of a random versus random bot. There's no kind of structure that they can learn against, and there needs to be a more methodical way for RL bots to actually learn against itself, and that's where the idea of self-play comes in. So this instance is 2 RL bots playing against each other, but effectively they are kind of the same bots. So self-play is true, which means that at every iteration of the board, we are setting the parameters of this bot to be equal to the parameters of this bot. So they're pretty much the same bot with the same parameters every time it makes a move, and it's effectively learning against itself in a true manner. What's more revealing is that when we compare these bots in these different simulations against the testing environment, where we're not doing any learning or any training loops, and we're just simply playing against random bots in 1,000 games, we see that the first bot that was trained against the random bot sees an 83% win rate, which is compared to the 73 that we saw during training. And then the RL bot that played with no self-play saw only a 64% win rate against the random bots. But on the other hand, the RL bot that played self-play saw an 80% win rates against the random bot. So when we review some of the games that the RL bot that was trained on self-play is actually playing and the moves that they're making, there is somewhat of a clear preference toward a certain side of the board, and you can kind of see there's not really a strategy that the RL bot is employing. It almost feels like it's learned to simply just place pieces in certain columns because against a random bot, that's just what works. That's what has worked because it's a very easy opponent to play against. This phenomenon is even worse in the RL bot that was trained against a random bot because the effect is essentially amplified. You can see this column, the bot really likes this column 5, and it just simply places all its pieces in there, or most of its pieces, because that's just what works against a random bot. So this is something we're gonna explore again in the next video. But yeah, it's interesting to kind of see what it's doing here. It's not very good, but you know, it's something. It's up to us to adjust the parameters, adjust the training, and the opponents that it sees in order to improve its learning. We are effectively the teachers of this RL bot, and that's what's so beautiful about these algorithms and this code, is that we can make anything of it. And yeah, I'm excited for the next video, but for now, enjoy these games by the RL bots, and I'll see you in the next one. Thanks.